All right, so let's begin. So this is called linear prediction of speech, linear predictive coding of speech. And what I want to do next is just formulate this into the same framework that we've just derived up above, right? So we want to derive the solution to A's, right? We want to determine those A's which minimize the mean squared error. And what do I mean by the mean squared error? So, so we wish to determine, choose these A1, A2 through AM such that what is minimized? What do you think? Kyun Ali? What do you think should be minimized? What should be the objective function?
So xn.
Xn should be minimized.
No, sir, error. Zn.
Error, right? Error
should be.
error. So error is what? Xn minus xn hat, right? But you want to minimize the second moment of that, right? So the squared error. You want to minimize the squared error. So this is xn minus xn hat. This is what you want to minimize. Is minimized. Right? So if I just try to draw parallels to what we've done up above, right? I can do that by just simply saying, the y that I had in the previous problem is x sub n in this problem, right? And the x bar that I had in the problem up above is this vector, which is x n minus 1, because these are the observations that I'm using to predict, right? X n minus 2 and all the way up to x of n minus m. And Windows has stopped. Hold on. Right. So this should be all the way up to x n minus m. And this is the transpose. Okay. And if you recall the solution that we had earlier from the problem or from the derivation that we did up above was A was equal to the correlation matrix inverse times P, right? Where P was what? Where P was equal to expected value of x times y, right? But in this case, what is x? X is just simply x n minus 1, x n minus 2, all the way up to x of n minus m. And what is y? Kyoji, what is y? Good. So mass is xn. That's correct. So this is times xn. Okay. And the expectation is outside of this, right? So this is equal to expectation. And this is the expectation over this vector. Okay, so this is P, right? Okay, so what I'm doing is, so this therefore is equal to expected value of xn times xn minus 1. This is xn times xn minus 2, all the way up to x of n minus m times xn. Now, here's the thing, which is k. So Khalid, scalar, what do you mean by scalar? Sorry, So xn, okay, xn is a scalar. Yes, that's correct, right? So that's why it can go inside the vector. It can multiply by each and every element of the vector. Okay. Now, I mean, if I were to describe this entire matrix, right, I would need m variable, m parameters of the statistical distribution to describe this, right? But for simplification and because of practical reasons, and we're going to find out that these processes are stationary. So what we typically do is we say, yeah, for these processes, Rk is defined as expected value of x n times x of n minus k. And these Rk's are independent of n. And a speech signal satisfies those properties, right? In other words, when I'm taking the expectation between two samples of the speech signal, right? That expectation, or I'm taking the correlation between two samples of the speech signal. The correlation between those two samples is actually a function of the separation between the two, and not on where I'm taking the sample at. Right? Do you get that? So a speech signal is a class of signal in which it is very, very practical to assume that the correlation between two samples of the speech signal is a function of only the separation between the two samples, right? And not on where the samples reside, right? So there's a function of the difference between the indices of where the samples reside and not on where the samples exactly are. Okay? So based on that, what can I say? Based on that, I can say this is actually equal to R1, right? Because the separation is just one sample. This is equal to R2 because the separation is only one, is two samples, and all the way up to Rm, right? Because the separation there is m samples. Okay? And typically, for signals like speech or some other signals, this correlation is actually decaying function. कि आप जितना past में जाते जाएंगे उतनी correlation कम होना शुरू हो जाती है. Okay. All right. What about Rxx? Right. So this is P. Right. So this implies that the P vector is equal to R1, R2, all the way up to Rm transpose, where these R's, R1 all the way up to Rm, are either going to be used from some speech models, right? So there's some speech models that we know of, and that's going to yield for us what these R's should be, right? Or these could actually be estimated from empirical observations. And in the past, I've actually assigned this homework problems where you would have had to estimate these R's and come up with your own linear predictive coder. Let's see if we can assign this this semester as well as a bonus, maybe, or as an extra thing to do. Okay? So these R's are something that's going to be made available to us, or these small R's are something that is going to be made available to us depending on what the speech model you're employing, right? And from them you can derive what P's are, right? P mil gaya mein, right? What's left is the correlation matrix. Okay. So what is the correlation matrix? So this is P, right? Let me just use this space here to talk about our XX inverse, right? What is that equal to? This is equal to expected value of X transpose times X, right? Actually, X times X transpose, right? And I know that X is whatever is this thing here. I mean, I've defined that. So this is expected value of xn minus 1, xn minus 2, all the way up to xn minus m times xn minus 1, xn minus 2, all the way up to x of n minus m, right? So what is the matrix that I get here? So what about the first row? First row पे क्या होगा? क्यों Zephyr? What are you going to get on the first row?
Sir, I was just confused that isn't this Rxx instead of the inverse, like as we defined?
Oh, sorry. So this is Rxx. Yeah, sorry.
So the first row is going to be x n minus 1 whole squared.
Xn minus 1 whole squared. What about the second term?
So in which direction exactly?
The row. I'm talking about the row. So this is xn minus
Oh,
1 times xn minus 2. Okay. So similarly, this is xn minus 1 times xn minus 3 all the way up to xn minus 1 times x of n minus m. What about the second row? Second row is going to be x of n minus 2 times x of n minus 1, then x of n minus 2 whole squared, and then x of n minus 2 times x of n minus 3 all the way up to x of n minus 2 dot x of n minus m all the way up to the last row, which is going to be x of n minus m times x of n minus 1 dot 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 all the way up to x of n minus m whole squared. Okay. Can I write this in terms of x zeros? Oh, sorry, r's, small r's. Can I write these in terms of small r's? So what is the first column, first row in terms of the small r? जी मोहसिन.
सर आपने बताया था कि ये पोजीशन पे डिपेंडेंट नहीं होते आर केस, तो वो आप आर जीरोस आपके डायगोनल पर आ जाएंगे.
Excellent, right? So there's going to be R0 here, and all the diagonal entries are R0s actually, because they're only a function of the differences, and the difference in all the diagonal entries is zeros. Okay. What about this? The first row, यहाँ पे the difference is R1. Okay. And then the difference is 2, and so on and so forth, right? All the way up to R of m minus 1. So this is R0. Okay. At the same time, this is R1, this is R0, and this is R1 again, all the way up to R of m minus 2. Okay. And all the way at the end, this is going to be R m minus 1 dot 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 all the way up to R0, right? So there's a symmetric matrix, and this is Rxx. This is the correlation matrix under this model, right? And now you have all the information that's available to you to come up with your speech codec, right? Or the speech prediction, right? And Gmosin, go ahead.
So could you scroll down a little bit? वो interface से cover हुआ हुआ है matrix.
Okay. Here you go. Okay, so this is Rxx under this model. This is P here under this model. Okay, and from here, all I need is to compute A. This turns out to be Rxx inverse that I've computed from the model times P that I computed from the model, right? And if I get to assign that MATLAB problem or homework problem, you will actually be able to see, okay, when you generate this prediction, the error that you're going to have, this L2 norm or the second moment of that error is going to be much smaller than the second moment of the speech sample anyway, right? So that means the prediction is good based on the model that you have developed. Okay, so there's a practical way of doing it, and hopefully we'll be able to see it in the last homework problem, okay, which is going to be optional. Okay. All right. Any questions here? No questions? Okay. So we have some time. So let me start with a new topic here. Right. So this is actually chapter 7 now. So chapter 6 and chapter 6, 7, like I told you earlier, I've lumped them together into a single discussion. Okay. And I am not going to discuss a lot of things from chapter 7, right? So there's some elements of chapter 7 that I've picked up, which are somewhat related to the estimation and principles that we've talked about. Okay. So the first thing I want to talk about is something which I've actually covered in some form or the other. So this is IID random variables. The definition of something called IID random variables. So who's familiar with IID? क्या होता है IID random variables? Somebody other than Mohsen? Zephyr, are you familiar with IID? The term IID?
Yes, sir. Independent and identically.
Yeah, independent and
I can't remember what D stood for, but
identically distributed.
distributed. Yes.
Right? So that means that if there's a sequence of random variables, right, which are drawn from the same distribution, right? So that means they're identically distributed, but they are independent of each other. Then that sequence of random variables is called is IID, right? So that's something which is very, very commonly used, right? So x1, x2, all the way up to xn are IID if they are all drawn from the same distribution and they are all independent. Now here's a common mistake or a misunderstanding that people have. When you say KG, if I say KG, let's say for example, all of these x's, x1 through x sub n, are drawn from the same standard normal distribution, right? They all of them follow the same standard normal distribution, right? What does that mean? Does that mean that the random variables are the same? Right? It does not mean that. It does not mean that the random variables are the same. In fact, they are independent of each other. So x1 is not dependent on x2, is not dependent on x3, and so on and so forth. However, their statistics are the same, right? So they have the same mean, they have the same variance, right? And not only that, they have the same PDFs, right? Or the PMFs, right? So that's what is meant by that they are identically distributed. This does not mean that they are the same, right? In fact, they are independent of each other. The one does not affect the other. Okay? So that is, so for example, I could say, okay, yeah, so we could say, okay, a Bernoulli random variable, right? So COVID-19 के case में, and perhaps not a very good example considering that there's so much tragedy around there. Like, let's say there's a random variable which talks about whether a patient is going to die or not. Okay, so if you're talking about death rates, right? So the death occurring or not occurring in a patient is actually a Bernoulli random variable, right? And we can sort of claim that Bernoulli random variable is independent across the patients. Okay, which is with a certain probability. We don't know what that probability is, and there are ways of estimating that probability, which all of our discussion will ultimately lead to. Okay, but they are identically distributed in the sense that they are all drawn from the same Bernoulli trials, right? Whether a patient is going to die or not. Okay? But they're not the same, because if there's one patient that dies, that does not affect whether the other patient is going to die or not. Right? And that's a modeling assumption we can make, right? Okay. And similarly, I can say, Keji, I mean, there's a white noise, there's a random electronic noise, right? There's thermal noise in an electronic component, and that's actually a process in the sense that that's a signal. And I say, Keji, I sample the signal at time 0, and then I sample the signal at 1 second, and then 2 second, and 3 second, and 4 second, right? All of these samples are actually going to follow the same normal distribution. Yet, all of these samples are going to be independent of each other. And that's another example of IID samples. Okay. Now, for these IID samples, let's say these X1s and X2 and X3 all the way up to Xn are in fact drawn from the same distribution, a standard or same, they're identically distributed and independent of each other. The question is, first of all, about mean estimation. Okay, so let's talk about mean estimation first. And the problem statement is the following. Given observations on x1, x2, all the way up to xn, can we estimate mu equals expected value of x I? Right? In other words, कि कोई एक डिस्ट्रीब्यूशन है जो हमें नहीं पता क्या डिस्ट्रीब्यूशन है, right? उसका मीन नहीं पता, लेकिन I have observations available. Can I try to estimate the mean of that distribution? Right? Which is the same as saying, for example, कि random variable these x could be age, right? The lifetimes, okay? The time to failure, right? And I draw and different bulbs time to failure सारे मैं observe करना शुरू करता हूँ. Bulb A का 1 का क्या है, bulb 2 का क्या है, bulb 3 का क्या है, bulb 4 का, and so on and so forth, right? All of these lifetimes are actually drawn from some distribution, and all of these distributions, all of these random variables are identically distributed. So that means they all have the same mean. All of the distributions have the same mean. The question is, given these observations, can you try to estimate the parameter that is mean? And yes, x are scalars. Shoaib, they are scalars. So what do you think? How do I estimate the parameter here? And if you recall, I mean, this discussion is actually linked with the previous discussion when we said the estimation problems. There are two types of estimation problems. One in which you're trying to estimate something which is random, and two in which you're trying to estimate something which is not random, which is deterministic yet unknown. And this is a class of that second. This is one of those problems in that second class. Okay, where you're trying to estimate a parameter which is mean, which is not random, but which is unknown. Okay? Achha, so given these observations, kya kare? I mean, how do I estimate the mean? Okay, so there's a very, very intuitive answer to that. Before I talk about the intuitive answer, let's do an example here. And that example is, okay, let xi follow a Gaussian distribution with a mean mu and a variance sigma squared, right, for all I. Okay? And actually, I can actually say this, okay, x follows a Gaussian distribution with a mean mu times 1, actually. And times sigma squared I. इसका क्या मतलब है? Huzaifa, because you asked me this question once, so I'm going to put you on the spot. So what does this mean? Okay. Anybody else? जी शोएब.
Sorry, ये आप ये outer product को पूछ रहे हैं ना?
हाँ, ये x का मतलब क्या है? ये, I mean, what is the statement that I've written?
Okay,
What
so
that
it's a
mean?
normal distribution. So mean जो है इसका sum of all the mu's है.
Yeah.
And okay, and so ये कहते हैं इसकी जो वेरिएंस जो है फिर एक मैट्रिक्स होगा,
Yeah, and what is that matrix?
आइडेंटिटी मैट्रिक्स जिसकी जो डायगोनल पे जो है हमारे पास सिग्मास पड़े हुए हैं.
Sigmas पड़े हुए हैं. So and so that means that the off diagonal entries are 0, right?
Yes.
That means in the terms, इसका मतलब ये है कि correlations जो हैं बाकी सारे random variables की आपस में 0 हैं.
And that means independence.
That means independence, right? And not only that, all of the diagonal entries on these of the correlation matrix or the covariance matrix are exactly the same. They're all sigma squared. ठीक है, इसका मतलब variances are the same for each and every one of the random variables. And what this mu times 1n means, okay, this is actually a column vector and each and every one of the elements of the column vector is equal to mu. So the means are identical as well. So this is really a depiction of what that IID stands for, right? So these are IID Gaussian random variables, right? All of them are independent and all of them follow the same distribution, which is Gaussian with a mean mu and a variance sigma squared. ठीक है, मोहसिन, क्वेश्चन?
सर इसको मैं कहना चाह रहा था कि आसान तरीका ये है इसको रिमेम्बर करने का कि आपको दो पैरामीटर्स चाहिए होते हैं, मीन और आपको कोवेरिएंस चाहिए होती है. तो जब जॉइंटली गाउसियन है और इंडिपेंडेंट है सारे गाउसियन रैंडम वेरिएबल्स, तो डायगोनल एंट्रीज सिर्फ आपकी सिग्मा स्क्वायर्ड होंगी और बाकी सारी नॉन जीरो होंगी. तो ये आसान तरीका है रिमेम्बर करने का.
एग्जैक्टली बट दीज रिमेंबर, अगर ये डायगोनल पे एंट्रीज आइडेंटिकल ना होती तो दिस वुड नॉट हैव बीन आइडेंटिकली डिस्ट्रीब्यूटेड, बट दीज आर आइडेंटिकली डिस्ट्रीब्यूटेड बिकॉज देयर इज एन आइडेंटिटी मैट्रिक्स देयर. ठीक है, and not just any diagonal matrix, it's an identity matrix. Okay, acha, now given this, can we estimate the mean? Estimate the mean given x1, x2 all the way up to xn, or given observations on. So how do you propose estimating that? Can we use maximum likelihood here? I would want you to use maximum likelihood estimation here. ठीक है, जी मोहसिन?
सर एक नाइव अप्रोच थी मेरी थोड़ी सी. अगर सारे रैंडम वेरिएबल्स को ऐड कर दिया जाए और नॉर्मलाइज कर लिया जाए तो आपको एक एवरेज वैल्यू मिल सकती है.
Okay, that's where I will head to, and that's a very very common estimator. Again, I just want to start out with the maximum likelihood principle first. Okay, so I'd say I will try to determine the maximum likelihood estimate of mu, and that's just simply the argument max, that mean or that parameter mu, which maximizes what? That maximizes the likelihood of the observations given mu, whatever that mu is. Okay, and this turns out this is equal to argument max, right? And I'm skipping steps here, so this is e raised to power minus xi minus mu whole squared divided by 2 sigma squared, right? So there was a 1/2 pi sigma squared product or raised to power n by 2. We don't need that because it's just optimization of that's just a scalar. Okay, and this optimization is something we've done, right? Iska kya solution tha? So you need to optimize this over y, and this is exactly the same optimization problem that we did in the temperature sensing problem, right? And it turns out that this is equal to 1 upon n summation I equals 1 to n xi, right? Or this is called what? This is called the sample mean, which is perhaps, Mohsen, your solution, right? Mohsen, was this your solution? The naive solution that you said, Kitty, I'm going to make a naive solution.
Yes, sir.
Okay. So it turns out that naive solution that you mentioned, which is actually makes sense. I mean, that's the first thing that comes to mind. If I say, Kitty, I've drawn from a particular distribution and I wish for you to compute the statistical average. ठीक है? In order to estimate that statistical average, the first thing that your mind tells you is to take up all of the samples and take the average. Okay? And that's called the sample mean. Okay, you have a sample drawn from a statistical distribution, okay, a sample from a population, and then you compute the mean of that sample, right? That's called the sample mean. And that turns out to be a good estimate of the actual statistical mean, right? Because of reasons that we're perhaps going to do in the next class. Yes, we are going to do in the next class. Okay. But the reason for putting this example up is that when the random variables are Gaussian, the sample mean is actually the maximum likelihood solution as well. Okay. So the sample mean, let me conclude this. The sample mean is given as Sn equals 1 upon n summation I equals 1 to n and xi. Right, so this is the sample mean. Okay, and it turns out, KG, this is turns out to be a good estimate of mu, which is equal to expected value of x when n is large. And what are the reasons for this n is large, we're going to see in the next class. Right? When they are Gaussian distributed random variables, it turns out the maximum likelihood solution भी यही बनता है. Okay? All right. So I'm going to stop here and maybe pause for any questions, or stop for questions here before we end. Okay.